State the number of complex zeros, the possible number of real and imaginary zeros, and the possible rational zeros for each function or for this function right here. What a mess, what a mess, what a mess, what a mess. Well, let's start out with complex zeros first. What is a complex zero? Well, a complex number is a number in this form right here. Now, if I were to pretend that that b is gone, then my complex number is real. If I were to pretend that that a is gone, then my complex number is imaginary. So complex numbers could be real or it could be imaginary. According to the Fundamental Theorem of Algebra, whatever your leading term's degree is the amount of complex zeros you're going to have. So in this case, we are going to have 5 complex zeros because this is a 5th degree polynomial. So that's part 1. Part 2 says if I'm going to find, let's actually jump to imaginary zeros before we do real. Part 2 says if I were to have an imaginary number, like a plus bi, I have to have its conjugate also floating around as my answer as well. So imaginary zeros, if you're going to have one, you must have the other. So I could have no imaginary zeros. I could have 2 imaginary zeros. I could have 4 imaginary zeros. So it's basically even numbers all the way up until you hit complex, but you're not allowed to go beyond it. So since my highest degree is 5, I start out with 4 and work my way down. Now what that means is since I could have 5 real numbers, I could also have 3 real numbers, and I could also have 1 real number. Okay, so whenever you're being asked to find your your real numbers, you start with the odds and work your way down from there. Now on to the nightmare scenario, the rational root theorem. Okay, the rational root theorem has me listing out every single possible root that is rational that I could have, and is an absolute god-awful nightmare. Okay, but this is what we do. We already have this written in order. I'm going to call you Q. It'll be nicer if I had a pen. I'm going to call you Q, and I'm going to call you P. Now, my rational roots are all the numbers in the form plus or minus P over Q, where P are all the possible factors of P, and Q are all the possible factors of Q. So what are my factors of P? 9, 3, and 1. What are all my factors of Q? 15, 5, 3, and 1. Now what I'm going to do is I'm going to list out all 12 possible numbers in the form P over Q. Technically it's 24 if I throw the plus or minus in there, so let's go in order. Plus or minus 9 over 15, 9 over 5, 9 over 3. We'll simplify these in a little bit. I'm going to forget my pluses or minuses. Don't want to do that. And 9 over 1. Now, I'm expecting repeats to take place. Okay, so if you're looking at this and saying, will we have 12 separate ones? Nope. When things simplify, we will have repeats and we'll get rid of the repeats. Okay, now let's do 3 over 15 plus or minus 3 over 15 plus or minus 3 over 5, plus or minus 3 over 3, plus or minus 3 over 1. Now let's do plus or minus 1 over 15, plus or minus 1 over 5, plus or minus 1 over 3, plus or minus 1 over 1, running out of space. All right, so let's write these all out. and get rid of the repeats. Let's simplify while we're at it. Plus or minus 9 over 15 can be written out as 3/5. So we're done with u. Plus or minus 9 over 5 is simplified as much as it can be. Plus or minus 9 over 3 is 3. Plus or minus 9 over 1 is 9. Plus or minus 3/15 is 1/5. Plus or minus 3 over 5, I did already. Plus or minus 3 over 3 is 1. Plus or minus 3 over 1, I did already. Plus or minus 1 over 15. Plus or minus 1/5, I did already. Plus or minus 1/3. And plus or minus 1, I did already. So these are my options, all of them in all of their glory. Do I have to put them in order? Nah, I'm not going to, but I did it. That's the rational root theorem. I sprinkled in some fundamental theorem of algebra in here. A lot going on in this one little problem, but we did it, and I'm proud of you.